Hi everyone, this is Nagendra sir. Today I will going to explain you crystal field splitting pattern in linear complexes, d-orbital splitting in linear complexes. This is the topic where I am explaining you from last 1 week, 10 days, right? In different complexes, we are gone through the d-orbital splitting, right? As such, octahedral, tetrahedral, square planar, trigonal, and distorted octahedral. These are the complex we have already discussed. Now I will going to explain you in linear complexes how the linear complex uh, get the d-orbital splitting. The linear complex is the two coordinated complex, right? This is what the linear you can write in left to right. I am writing into uh, front and back, or you can say that top and down, right? So the linear complex is two coordinated complex ml2, right? This has centrally situated metal ion and above and below the two ligands occupy two corners of the linear, right? Here if we incorporate coordination axis, the z-axis will pass us through all the atoms, all the composition of the complex. That is what metal and two ligands. The x-axis will pass us through only metal side. The y-axis will pass us through also with only one metal side, right? This is z, this is y, this is x, right? That's how we have to consider the coordination axis. Along the two ligand sides and metal, we will go with z axis. In insertion of x y z coordination axis, z axis passes through all the two ligands and metal ion from above to below, right? The x and y axis passes through only metal ion, only metal ion, right? So that's how the coordination axis, ligand orientation with respect to all three coordination axes, right? Now here, when we go with the splitting pattern, as we every time starting, free metal ion, d orbitals, thus get excited in complexation, complex d orbitals, and where here the splitting will takes place. Right. So that's how the d orbital splitting. Taking similar of last splitting pattern, taking dxy orbital. The dxy orbital, right, has lobes in between the xy axis, which they the lobes will be away from the ligand sites, right? The ligand sites, how they are here in linear complex, they are along the z axis, right? Nowhere on the x or y or in between the x and y, right? So the lobes of dx and y, which are in between the coordination axis of x and y, will never be have any interaction with ligand sites, right? So having no interaction with ligand sites, the dxy orbital gets stabilizes, reaches to lowest energy, right? Now we are going with next orbital, dyz, right? The dyz has the lobes in between the z and y, right? The lobes are in between the z and y, right? Consider, right, consider this, right, this pen which is above and below, as it is linear complex. At the middle it has the metal, the above one ligand, below another ligand, right? That's how you have to consider. So here, left and right x-axis, front and back y-axis. On left and right there is no ligand sites. On y and on y-axis also there is no ligand site. And here, what we are consider the x and y, the dx and y has a lobe of here and here and here and here, where the ligand is above and below. So these above and below ligands cannot be interact with these two orbitals or these two orbitals of xy, dxy. So have uh, the dxy orbitals are totally, we can say that they are totally away from the ligand side, which are above and below, right? So far it is reaches to lowest energy level. Now coming to dyz, dyz, the y is front and back, the z is above and below, the z is above and below, y is front and back, right? The lobe is how here, dxy lobe, sorry, dyz lobe, it is here, right? In between the z and y it will be here, right? And this is y, this is z, so here it will be, right? Here will, here one, same to that below side also, here, here and another, right? So consider these two lobes, right? They are slightly near towards the this particular z axis, right? Having near to z axis will also near to ligand side, above and below, right? So far the nearby lobes of dyz, right, with the ligand side will have slightly sidewise interaction. Very partial sidewise interactions here it can be have, right? Having closer, slightly closer towards the ligand sites, sidewise interactions here it created, right? So far the slightly sidewise interactions, right, will get destabilizes the dxy in a slight extent, right, to exact very little amount from the zero state. Here it will come dyz. Since the lobe of it is slightly towards the ligand sites, which is along the z-axis. So far it has interacted with in sidewise in partial, will get slight excitation, from the zero state, right? Same to that, the lobe of now you consider the orbital of dzx, right, which has the lobes in between the z and x orbital, z and x coordination axis. Left and right will be the x-axis, and above and below will be the z-axis, right? There the lobes will be in between the x and z, here and here, and below 2, right? So this particular lobe, which is xz, in between of x and z, here it will be, and here another lobe, right? These lobes also, the lobes of the dzx also having closer, slightly closer to the z-axis, right? So far it can also closer to the z-oriented ligand sites, right? So having slightly closer towards the ligand sites of these two lobes of and donor lobes of the dzx will have again sidewise partial interactions such as the dyz, right? So far thus same, the dzx also will reaches in a slight excited as such of dyz will create a w degenerate energy level at the slight excited level, excited energy, right? Next coming to dx square minus y square, right? Here dx square minus y square has the lobes along the x-axis, along the y-axis, right? X-axis is left to right, y-axis is front and back, right? So on along the x-axis there is two lobes, here one, here two. Along the y-axis front and back there are another two lobes, right? These four lobes of dx square minus y square on here, where the ligand is above and below along the z-axis, right? So these particular z-axis and its oriented ligand sites are totally away from the dx square minus y square, right? Or we can say that the dx square minus y square orbital lobes are totally away from the z-oriented ligand sites, isn't it, which is above and below, right? So far these two cannot interacting with all the four lobes of the dx square minus y square, will stabilizes the dx square minus y square in an lowest energy level, which is same as the dxy orbital lobe, so reaches to lowest energy level, right? So here these together dxy and dx square minus y square will creates the lowest energy level at the doubly degenerate energy state at the lowest energy level, right? And finally the dz square orbital lobe. The dz square orbital lobe, we know that it has along the z-axis two lobes, at middle there is a spherical lobe, right? So the dz square, as it is along the z-axis and which is along the z-axis, there are two, all the two ligand sites existed by the linear complexes, will create them extreme interaction, negative interactions of ligand site with dz square orbitals. So these extreme interaction of the dz square orbital with the ligand site, two ligand sites of the linear complex, will destabilize the dz square orbital in an extreme level, will make excitation of dz square orbital in an highest energy level, and which goes far away from the all the orbitals, other orbitals, and reaches to highest energy level of here, right? So like this, the all five orbitals, non-degenerate orbitals of d orbital metal complex will get splits into three energy state. Two are doubly, one is singly degenerated state, where these newly generated energy levels will symboled with Mulliken symbols, where singly degenerated energy level symboled with A1G energy state, and doubly degenerated slightly excited energy level will represent the E double bar G energy state, and lowest energy level doubly degenerated energy level will indicate with A bar G energy state, Mulliken symbol, right? The energy excitation of dz square orbital will be 10.28 dq, and slight excitation of doubly degenerate energy level of E double bar G will be 1.14 dq, and lowest energy level of E bar G will be lowers its energy by minus 6.28 dq, 28 dq, right? So that's how the splitting it taken place in the linear complexes. So in description, what we can write is the dxy and dx square minus y square orbitals in linear complex are away from the all two ligand sites. So stabilizes by minus 6.28 dq energy and generate E1G doubly degenerate state, right? In second statement, the dzx and yz, dyz and zx orbitals has have lobes slightly towards z axis oriented ligands. So these have sidewise partial interactions and destabilizes these will generate E double bar G doubly degenerated energy level with 1.14 dq energy. The dz square orbital has along the z-axis has lobes along the z-axis which can direct directly interact with ligands. So get destabilized and excited to 10.28 dq energy level of singly degenerated energy state. A1G. Right. So this is how the uh, d-orbital splitting pattern in linear complexes. So here I stop. Hope this will be giving you better explanation of d-orbital splitting pattern. One more time I am giving you the splitting pattern. The linear complex having 5 degenerated non-degenerated d orbitals will get splits into 3 energy states. One is singly degenerated state, two doubly degenerated states. The dz square orbital having lobes along the z-axis along the ligand orientation has more repulsive interactions with the ligand sites will get destabilizes in an extreme level, reaches to higher energy level of A1G energy state, that is 10.28 dq, and the dyz and zx orbitals has the lobes in between the zx, zy and xz orbitals which are slightly towards the ligand side, has partial interactions with the ligand sides, will partially destabilizes, reaches to a double bar G energy state which is 1.14 dq, and the other two, the dxy and dx square minus y square orbital, has the lobes along the x-axis and in between the x and y axis will be all away from the ligand sides, right? So thus away from ligand sides will make stabilization of the two orbitals in a lowest energy level of a bar g, sorry, e bar g energy state which has minus 6.28 dq energy state. So this is how the d orbital splitting pattern in linear complexes, right? Thank you.